So I'm Dorsa, and my research is about designing algorithms for autonomous systems and robots that safely and reliably can interact and collaborate with people. So I'm interested in systems that I should probably be here, right? Oh, yeah, okay. I'm interested in systems that look like this. So you can think of robotic surgery or autonomous or semi-autonomous driving, or let's say controlling drones from the ground, service robotics, like assistive robotics at home. And these systems might look very different from each other, right? They're very complex. There's a lot of engineering into all of them, and they seem quite different. But they have one major thing in common, and that is they're all safety critical, and they all need to interact with people. So if you're designing algorithms for these systems, we should really think about the safety aspect of it. We should really think about the interaction that goes on between the robot and the human. So the systems I'm usually interested in look like we have a robot, or we have multiple robots, and we have a human interacting with them. And the core problems that we think about are about safe and interactive autonomy. And then these problems lie at the intersection of a few different fields. Of course, we want to do machine learning. Of course, we have a lot of data. We want to learn models. In addition to that, you want to control the system. So we need to care about how the actuation should work, or how should an autonomous car actually drive. But even that we have those as part of these systems to get them even right, in addition to those, we have a bunch of other things. We have humans interacting with these systems. So we need to think about human-robot interaction. We need to think about how to model humans. Like, what sort of computational models should we actually use when we think about these interactions? And that brings actually a lot of questions about safety too, because these systems are interactive. They're at homes, or they're on our roads. So we need to think about the safety questions there too. And from that perspective, we're interested in applying things like formal methods and verification and validation for some of these human-robot systems. So to be able to give guarantees about them. So Michael talked a little bit about that, but we, as part of a group, we are thinking about how to apply more formal techniques to talk about correctness of some of these systems. So currently in my lab, we're thinking about a few different directions. Some of the things we are looking at are about shared control and collaboration and coordination between humans and robots in home settings. So for that, we think a lot about safe control and how the human and robot should bring their control inputs together to do a task safely. And in addition to that, since we're working with humans, as I mentioned, these models of humans is really important. We need to build really good models of humans to understand complex goals of humans and to infer like what they're doing, like what object are they going for, what is their intent. So intent inference is also a big question that we try to answer, building good intent models, goal models from the human. And then if we have that, then from a robotics perspective, we should also try to do tasks in a legible and expressive way so the human can understand which object am I going for, where am I driving towards. So we're really thinking about this interaction and adaptations that can happen over time between humans and robots. And then while doing that, well, we care about social navigation. So we care about how, like in terms of navigation, we care about how robots navigate around people, how autonomous cars should drive around multiple people. And also, again, there's a big safety issue when we think about these systems too. How are we going to safely learn? Like, as we are driving on a road, we're going to get more and more information about humans around us. How are we going to safely learn that and safely explore that? So we have the same issue of exploration and exploitation that comes up in a lot of robotics and machine learning applications. But we now actually need to do it safely because if we don't, like, we can't afford losing a robot, or we can't afford losing an autonomous car. We actually need to be very careful applying safe learning techniques. So these are some of these major directions we are thinking about. And in terms of application, we are interested in driving, we are interested in human-robot interaction. But I wanted to just show one example, one driving example that we have been looking at to just motivate this a little bit more, like, why do we care about modeling humans? So today, if you think about autonomous cars usually try to optimize for reaching for their destination. And at the same time, they try to avoid unsafe regions of the road, like the boundaries of the road. And if there happens to be another vehicle on the road, they usually treat that vehicle as a moving obstacle. So basically try to do collision avoidance with that car. That's all they try to do. They look at the velocity of that car, they think where that is, and then based on that, they're done. They just try to do collision avoidance. But if you think about it, this vehicle that's on the road is not just a moving obstacle that happens to sit there, right? There's a human inside it. And the human has a model of the world and also tries to optimize for reaching for his destination. So whether we want it or not, or whether we plan for it or not, the actions of this autonomous car, the orange car in this case, can actually affect the actions of the human-driven car. And that has a lot of safety implications. So for example, if you want to change lanes, you don't just like cut in front. What you do is you start nudging in front of people, and you kind of expect other drivers to slow down and make room for you. If you assume that the other car, in this case the black car, was just driving with constant velocity, you would never be able to do something like that because you want it to be safe, and you would never be able to like cut in front of people. The way you cut in front of people, where you achieve your goals, is by nudging in. And how can we do that? Well, we have models of humans, right? We have a model of how this black car is going to drive. And we have a model of how this black car is actually going to respond to my actions. And because of that, I can actually achieve this task, and I can do that safely. But the way our autonomous cars work today, this is actually a recent video from Waymo. So look at the Waymo car. The Waymo car tries to change lanes, and it even like turns its signal on. So you expect like other drivers are going to be nice and are going to actually like create some space maybe. But what happens is, like the Waymo car is not actually able to change lanes because it doesn't have a model of the human-driven cars. And because of that, it actually has to like exit and come around and do it again. So this is kind of like the state of the art. Like this is what our cars do right now. And they don't really take into account the fact that there are humans around us, and these are intelligent agents that are responding to our actions. So motivated by that, my group usually thinks about interaction when we think about planning for autonomous cars or robots. Interaction is a big component that comes into our planning and algorithms. So for example, when we think about autonomous cars, we think of interaction of the overall system as a dynamical system. We think of an autonomous car working with a human-driven car. And there are a lot of questions that still exist, and a lot of questions in this one slide that we're very interested in answering. So for example, you want to plan for the autonomous car. You want to figure out what should be the actions of the orange car. How should we do that? Well, one way of doing that is maybe assuming that this autonomous car, this UR started policy of autonomous car, is a maximizer of some reward function. Well, what should be that reward function? Like, how are we going to encode safety in that reward function? How should it balance these different objectives that we have in an autonomous car? What is a good thing to optimize for an autonomous car? How do we make sure like not unsafe things won't happen if we optimize that? And how do we even like bring in models of humans in that optimization? So right now I have that UHS starter, which is policy of the human. I'm saying this reward function should depend on policy of the human, should consider interactions. But what is even UHS? What is the policy of the human? Like, how do we know? How can we build predictive models of humans? So in our work, what we do is we actually model humans as agents who are approximately optimizing their own reward function. We assume they have some objective and they're trying to optimize that. But that's not always a good assumption. When it comes to near accident scenarios, humans don't do that. Humans don't optimize objective functions. So how are we going to address these safety issues when we are close to, like when we are at near accident scenarios? And is optimizing a reward function a good model? Should we put a neural net there? How should we model, again, humans UHS starter and think about this interaction? Again, a lot of questions in this one slide. And another thing that we actually started looking at, like along the same lines, is we think that we should always like do an online learning, have an online learning fashion which tries to update its models as it goes. So another variation of this formulation is, as I'm trying to achieve my tasks as an autonomous car, maybe I should be curious about the humans around me. Maybe I should encode that curiosity in my formulation. Maybe I should have a term about information gain, how these other drivers around me drive. And actually, by encoding that, what happens is our autonomous cars take an action that's similar to that. They start nudging in. They don't like just cut in front of people. They start nudging in to see how the other drivers respond. And based on that, they decide what to do next, which is kind of interesting because this was just, again, out of the optimization. Nothing was hand-coded here. And it was kind of interesting by encoding curiosity into our formulation, we can see these interesting behaviors. And another point I want to mention, again, on this formulation is, even if we get everything right, let's say we get everything right, we have good models of humans, we can predict what humans are doing, we can figure out what should be the reward function. Even if we get everything right, what can happen is we might not be able to find a set of actions for the autonomous car that's safe. Because we have a set of safety constraints, right? We might just not be able to find that. And that's not a crazy idea. Like even Google, that's trying to go fully autonomous, they have around 300 disengagements per 400K miles of driving. So that's about one disengagement per month for a typical driver. So if we want to have these many disengagements, these many situations that we don't know what to do, we should have a better way of handling that. We should have a better way of maybe transferring control to the human. Maybe that is not the right thing. Maybe that is the right thing. But we should actually have a better way of handling these near accident scenarios or these situations that we don't know what to do. And finally, another direction that we are interested in, and it has connections to safety, is the multi-agent implications of this work. So imagine we have now multiple autonomous cars and multiple human-driven cars. Let's say I have multiple trucks on a road and multiple human-driven cars. So in this shared road setting, it's interesting to think about how the interactions should go. Maybe the autonomous cars can actually guide the humans for better traffic or for better social kind of values that we care about. Like, it's interesting to think about the social implications of these multi-agent systems. And other issues come up too, like things like fairness. Like, let's say that my autonomous car knows how to cut in front of the people. So if it does that with one car, if I multiply that by 100, the outcome is all the autonomous cars are now going to get in front of the human-driven cars. And is that really what we want? Like, do we want that type of implications, or do we want our autonomous cars to guide the human-driven cars on the road in a better way for better social outcomes? So these are some of the directions that we are looking at. And a lot of these questions, I've talked about them in the setting of autonomous driving, but they also apply in other autonomy settings in human-robot interaction. So we're interested in both these directions. And this is my group. I just want to put a picture of the group and our robot. And I'll end now.